everybody. I'm glad to be presenting this talk today on From Pixels to Products, an overview of satellite remote sensing. My name is Sundar Christopher, and I am a professor in the Department of Atmospheric and Earth Science at the University of Alabama in Huntsville. So at the bottom of this graph, you will see electromagnetic radiation. This shows increasing wavelength and increasing energy in reverse directions. And it is electromagnetic radiation from the sun that makes satellite remote sensing absolutely exciting. And today, for most of the talk, I'll be focusing on mostly the visible, the near infrared, and the thermal infrared part of the electromagnetic spectrum. So I feel that I'm at a stage in my career where I can tell a little bit of a story on my journey and how my journey got started. And in order to do that, here is a background picture of aerosol optical depth. My research is in the area of satellite remote sensing of aerosols for both climate and air quality purposes. And then you can see here the dust storms in Africa and then biomass burning. You can see in South America and in Africa as well, and various forms of pollution, and then you have sea salt aerosols here. So in that background, I thought I'll give you a little bit of where I am from. So I was actually born in Coimbatore, India, 11 North and 77 East, a long time ago. And it was absolutely in the tropics. And interestingly enough, I moved to Rapid City, South Dakota. Take a look at the latitude, which is 44 north and 103 west. I had never before seen snow in my life. So when I arrived there in August, it soon got pretty cold. And then I saw snow and blizzard for the first time. That was an interesting experience. And then I finished my master's in Rapid City, South Dakota. And then I moved to Fort Collins, Colorado. 41 north and 105 west, an absolutely fantastic place at Colorado State University. And then once I finished my PhD there, I went back to Rapid City, South Dakota for a short time. And then I arrived in Huntsville, Alabama with jet black hair almost 25 years ago. I've been at the University of Alabama in Huntsville for about 24 plus years now. And I started my career as an assistant professor working on satellite remote sensing. As an interesting anecdote, one of the fundamental reasons when we moved as a group from Rapid City to Huntsville was there was a lot of satellite data that was available. So that was one of the driving constraints for us to move to Huntsville, Alabama. So a couple of different places that I thought that I will, give you an anecdote about. One of my most favorite places to do research, of course, is Sydney, Australia. I spent a year there studying bushfires and wildfires there. Although there's very little pollution, as you can see from the map, there's a lot of pollution that is transported from other parts of the world into Sydney, Australia. And I, used a lot of ground-based instruments and satellite remote sensing. And by far, some of the most creative work that I have done in the past, I've spent about 3 or 4 summers at the UK Met Office in Exeter, and 50 North and 3 West. There is absolutely fantastic data that's available from the Met Office. They fly aircraft, they have ground-based instrumentation, and I provide the satellite perspective for that. So with that, let me give you a little bit of an outline for my talk today. I'll give you a little bit of an introduction on satellite remote sensing. I'll talk you through the fundamental units of measurement, which is radiance and atmospheric effects. Atmospheric effect is noise for some, and people study the atmosphere in other cases. And then I'll step you through some radiation laws. And then I'll provide some sensor characteristics, spatial resolution, spectral, temporal, radiometric resolution. We'll talk a little bit about signal to noise as well. And probably at the heart of satellite remote sensing, especially passive satellite remote sensing, is spectral signatures. And we'll talk about spectral signatures in different parts of the electromagnetic spectrum. And image classification is key, whether you're using simple techniques, thresholding techniques, or complex neural network or deep learning techniques. Separating an image into one of many classes is at the heart of satellite remote sensing. And then when we move from pixel to products, often a radiator transfer algorithm is involved, and I'll talk about the caveats and the pitfalls that are involved when using products. There are so many products out there. And we need to just be careful on how to use these products carefully. And then I'll talk a little bit about validation, and then I'll wrap up in terms of summary on what that looks like. So anyway, so that is going to be the scope of my talk for today.
So I think I have no idea who all is in this call, but I just wanted to get folks excited about an image like this. This is a fantastic global image. This is from Modis Terra. So this is red, green, and blue, which is 650, 550, 470 nanometer. It's basically a 3-band overlay. And at first sight, it looks pretty benign and it looks really great, but there are so many nuances and details. So for those of you who haven't taken a satellite remote sensing class, so here are a few pointers. Clouds look white, and we'll talk about some of the reasons why they look white. So this is a polar orbiting sun synchronous satellite, which means that as the Earth is rotating, the satellite faithfully goes in a circular orbit. And every day at the equator, it crosses at about the same time. That's why it's called sun synchronous. And the reason for that is if the image was at different times of day, then the solar zenith angle would be different, and therefore the image could look very confusing. So sun synchronous is a standard orbit for polar orbiting satellites. So when you take a look at this image, and I'm gonna try and see if my pointer works. Manil, do you see my pointer? Okay, you should now.
Yes, we do.
So, yeah, okay. So clouds look white here, and there's dust aerosols, there's smoke aerosols. You have to look really hard. And then these black missing spots are, just due to the orbital. There's in one day you get a global image, but there are slight gaps as well. So, and this is the Swath width. There's sun glint that's happening here. That there's so many things that's happening in an image. But if you take a look at this image, you have so many classes of features, if you will. And if you're a cloud scientist, you don't want to study water or land or smoke. So you need to be able to separate clouds. If you're interested in dust aerosols, you need the capability to remove this. And that's what we'll be talking a little bit about today as well. So there's several things that are happening. Atmospheric composition is aerosols, weather, climate, water and energy, carbon cycle, Earth surface. This is what encompasses the Earth atmosphere system, if you will, or that's how NASA classifies that. So, so it's very important to understand, some of these features in the satellite image. And on the left here, this is a geostationary sub-hourly image. So this is absolutely fantastic. We have 2 geostationary satellites, and we can get sub-hourly information, so we can study whether it's clouds or aerosols or other features. We can look at that as well. But I won't be talking a lot about geostationary data today. So at the right here is again, this is from NASA's satellite. You can see these red dots as fires. We'll talk about how you arrive at these red dots, and you see the smoke aerosols, and you see the land features in some of this image, and clouds are here. So this, again, looks very simple. But one of the things that scientists struggle with is, are the aerosols on top of the clouds or below clouds, or clouds on top of the aerosols? So the vertical distribution is important. And one type of satellite sensor may not provide all of that information, and therefore multiple sensors are often needed. A quick definition of remote sensing: the measurement of an object by a device that is not in physical contact, as opposed to aircraft data where you're actually flying through, whether it's clouds or aerosol, to make a measurement. So an active remote sensing, an example is LiDAR, CloudSat or Calypso. You have a signal from the satellite itself. It bounces back from the Earth atmosphere system back to the satellite. That's an active system. We won't be talking a whole lot about that today because of time interest. So a lot of satellites are sensors or passive remote sensing. It only receives radiation from a target of interest. What does this mean? The electromagnetic radiation from the sun travels through the atmosphere, hits the Earth's surface if on a clear day, if you will, and reaches back to the satellite. And this is passive remote sensing because we're not generating electromagnetic energy ourselves. So MODIS, Sentinel, and LANDSAT, and the majority of orbiting remote sensors are passive. So again, just as a piece of information, we'll be concentrating on multi-spectral satellite data today, but there's also multi-angle. An example is MISR. There's polarization data. An example is polar, but we won't be concentrating too much in the interest of time. Okay, so some basics. So I hope you stay with me here. So these figures are generously borrowed from different places, and some of this are on the common license agreement. So, so here is sun, and here is electromagnetic radiation that comes from the sun, and it hits the Earth's surface. So that's the incident energy, and a portion of that could be reflected back. Some of it could be absorbed, and some of it could be transmitted. So in all this says is this energy is conserved, right? So the incident energy must be equal to the reflected, absorbed, and emitted. So if you were to take a look on this side of the graph, I drew what the radiation, the energy spectrum is that comes from the sun. So if you were to assume that the temperature of the sun's photosphere is about 6,000 K, you see that the peak emission where the sun emits is at about 0.5 micron. So no wonder you have a lot of satellites that sense the reflected radiation in 0.5 micron because you have, high energy. So things are going to, look bright, if you will, if you sense in that part of the spectrum. So, and as you can see, as the wavelength increases, the energy decreases. So don't worry about the y-axis. I took the units off and the nomenclature off just to keep this simple at this time. So the next thing is the amount of solar radiation that is absorbed is now re-emitted by the Earth at a fundamentally different wavelength at 10 micron. So the peak of the Earth emitted radiation is 10 micron. And you will see that a lot of satellites sense the radiation at 10 micron. And there are reasons for that, because that's where the peak of the sun's electromagnetic radiation is. So, fortunately for us, less than 4 micron is seen as, the reflected solar energy. Greater than 4 micron is thermal energy, allowing us to do radiative transfer differently. So I've drawn this graph for the surface, but you can do the same thing for the atmosphere. So if you have atmosphere here, some of it could be reflected from the atmosphere. We'll see in the next graph as well. Okay, so just so that we don't get bogged down just by looking at equations and graphs, I just thought I'll throw up an old sensor, if you will, the Advanced Very High Resolution Radiometer, that basically had 5 channels, NOAA 6 to NOAA 8. So channel 1 is 0.58 to 0.68 micron. So this is often called the spectral width, if you will. So depending on who you talk to, if you were to ask what is the spectral resolution of AVHRR, people would say there are 5 channels. And others would say the spectral resolution is 0.1 micron. So the difference between 0.68 and 0.58 micron, and we'll talk about why that is important. So it basically has 5 channels. And as you can see, the peak of the sun's electromagnetic radiation is in this part of the electromagnetic spectrum. So that's why you actually view this. So again, here you don't have red, green, and blue like some of the modern sensors have. Channel 2, 0.75 to 1.1. And we'll look at why we need this channel. And then you have channel 3, 4, and 5. Key piece of information to keep in mind, channel 1 and 2, as I mentioned before, provides reflectance. We'll see a simple equation for reflectance. Channel 4 and 5 provide the temperature of the Earth and at the atmosphere. And channel 3 is a little bit tricky. It has both reflectance and temperature as well. Okay, so let's take a look at the right side of the graph. So the radiation that comes from the sun is given by this solid red line, and what reaches the surface is actually very different. So you see these little dips and peaks and valleys. So that basically is due to the absorption. So the radiation that comes from the sun is absorbed by water vapor, by carbon dioxide, by oxygen and ozone. And in some parts of the electromagnetic spectrum, all of that is being absorbed. So if you were to take a look at this, UV is absorbed in the top part of stratosphere and a little bit higher. So you see all of this is being absorbed. But then when you get to other parts of the electromagnetic spectrum, as I've drawn some arrows here, you see that the absorption is not very high. So this is what is called an atmospheric window. So the regions of the electromagnetic spectrum where the absorption and scattering is minimum is called an atmospheric window. So for example, 0.58 to 0.68 micron that the satellite senses radiation is in an atmospheric window. There's a little bit of absorption by ozone, but for primary purposes, it's an atmospheric window, which means that it's not, there's no interference from water vapor and carbon dioxide. So you can see the surface of the Earth much better. So that is what is called an atmospheric window. So things in the infrared part of the electromagnetic spectrum are a little bit nasty. As you can see, a lot of the outgoing energy from the Earth is absorbed by water vapor. So water vapor is the primary greenhouse gas, as you will. And then here you have 4.3 and 14.9 micron absorption bands for carbon dioxide. So each one of these atmospheric constituents has a certain absorption band, which is used for sensing. If you want to study water vapor, carbon dioxide, you would use these bands. So this is an absolutely important concept in satellite remote sensing, the concept of atmospheric windows, where the electromagnetic spectrum regions there's less interference due to absorption and scattering. Okay, so as I mentioned before, this is a complex process. I'm not going to get into all of the details here, but I want to highlight a few things. So the radiation that comes from the sun there's direct radiation that hits the surface, but there's also atmospheric constituents. And once it hits those atmospheric constituents, it actually is scattered in many different directions. So, and on the left here is a little bit of a cartoon, how these gases absorb, how these molecules absorb is a function of, electron, photon theory, and it gets really, really complex. But for our purposes, the key thing I want to leave you as an audience today is, so here you have the radiation that comes from the sun, and it's a clear day, it hits the surface, and the surface reflects a certain amount of radiation depending on what that surface is. And again, on its way back, there's a little bit of absorption, and this radiation arrives at the sensor. So what does the sensor see? The only thing that the sensor sees, the satellite sensor sees, we use MODIS or Sentinel or GOES-R as an example, or LANDSAT, it measures the amount of energy per unit time, which is watts, right? So the amount of energy per unit time, joules per second is watts, that comes from a square meter, which is a pixel, and steroradian is a three-dimensional radiance. So radiance is two-dimensional and steroradian is three-dimensional per micron, which is in a certain wavelength band. So that is all the satellite senses. So the key thing, again, to keep in mind without getting into the complexities is this watts per meter squared per micron per steroradian. When the sensor senses that, we need to know how accurate is that sensing. So that is where calibration comes into play. So this sensor, before it was launched in the pre-launch stage, there were a group of lamps. They would shine a group of lamps, if you will, on the sensor, and they would look at the response of the sensor from these lamps, and they would form calibration coefficients. So there's pre-launch calibration, and for the Earth environmental satellites, for most of them, there's also onboard calibration. So when a satellite like MODIS senses watts per meter squared per steroradian per micron, we know how good that value is. So it doesn't measure things like temperature or aerosol concentration. All it measures is spectral radiance. So in the infrared part of the electromagnetic spectrum, so remember that the energy that was absorbed by the sunlight is now emitted by the atmosphere, and water vapor, carbon dioxide, all of that absorbs in these layers, and it reaches the satellite as well. So again, it's a complex process, but the key thing to remember is, I mean, here's a spectacular image. I've been doing this for 3 decades almost, and I still get excited about looking at images like this. Earth sun distance is 1.5 times 10 power 11 meters, satellite altitude is 700 kilometers, and here is some spectacular imagery that has clouds, that has lands, and we measure that, within, a certain accuracy. And this basically is a graph to show you that the energy from the sun is shown by yellow, and the energy emitted by the Earth is shown as in red. And because the Earth emitted radiation is at much longer wavelength, the energy that comes from the Earth's surface is a lot less than energy that comes from the sun. So the other key thing to keep in mind is, when the satellite is looking at the spectral radiance, it's looking at it at the satellite level. Most people are interested in what the reflectance is at the surface, or the temperature or the thermal energy that comes from the Earth. But all we get is what is sensed at the satellite. So we need to subtract the atmosphere portion, which is the atmospheric correction piece. So again, quickly looking at, from measured radiance to temperature and reflectance. So key thing to keep in mind is the satellite measures a radiance. And if you use the Planck's equation, everything else is a constant here. In this equation, c is the speed of light, h is the Planck's constant, lambda is the wavelength in which you are sensing, and if you lambda, which is the radiance, the watts per meter squared per micron per steroradian that I talked about, if you know the wavelength in which you are measuring it, you can calculate the temperature. It's a very simple equation. All of my students go through this in class, and with a satellite measured radiance, you can actually measure what the temperature of that particular pixel is. So you can, calculate the temperature of the surface or the temperature of the cloud top as well. Manil, you can still hear me?
Yes.
Okay, good. Yeah, there's something on the screen that flickered. So, all right. So the second thing that you can get is reflectance. So here is the so this is in the temperature part of the electromagnetic spectrum. So here's the second thing that you can convert the satellite measured radiance to. The radiation that comes from the sun is reflected by this pixel. You can actually calculate what the reflectivity of that pixel is. And in the next slide, I'll show you why this is important. So this L sub lambda is measured by the satellite. The E sub S is a known value, which is the amount of radiation that comes from the sun at that particular wavelength. Everything has to be scaled by solar zenith angle, which becomes an absolute key. So again, key thing to keep in mind is the satellite measures a radiance. It can either be converted to temperature or it can be converted to reflectance. So why is this stuff important? So here on the x-axis on the left side of the graph, you have wavelength from 0.4 to 2.4, 0.4 to 2.4 micron. And then on the y-axis is surface reflectance. So this is the surface reflectance measured at each one of these wavelengths. And these gray vertical bars here show where some of the satellite wavelengths are. So this is what is called spectral signature. So if you were to take a look at this green graph, this is a healthy green vegetation has a fingerprint that you can actually, comes from a database, or you can actually, have an instrument that you can point at a vegetation and you will get this fingerprint. Similarly, you have things for water. If you take a look at water, the reflectivity of water is very, very low. It's less than 10%. So this is why water looks dark. So the amount of solar radiation that comes from the sun is reflected very little by water, and that's why water reflects dark. So clouds, the reason that clouds look quote unquote white, if you use red, green, and blue, is if you were to take the red, green, and blue, which is right here in this part of the electromagnetic spectrum, you will see that they are spectrally flat, if you will. So they reflect very high values, but they're spectrally flat. So if RG and B is the same, if your gray level values are very high, and if they're the same, they're going to appear white. So these are some of the fundamentals that becomes very important when interpreting some vegetation is near IR values. So for just about anything in the Earth feature or the atmosphere feature, these are some of the fingerprints. And the other things to keep in mind is, the water vapor absorption shows up in some of these bands, which we're not going to talk about a whole lot today. So on the right side, I wanted to make sure that I mentioned some of you are working with hyperspectral imagery. So this is hyperspectral imagery from AVIRIS. So rather than having 8 or 10 or 15 bands, here are 224 bands. And this is an airborne visible infrared imaging spectrometer. And here is a graph that says LANDSAT 8 and 9 has these bands in the red, green, and blue. And here are these discrete values, whereas you have 224 bands of AVIRIS. So there's a lot more information content that you can get from hyperspectral imagery. So very quickly to go through some of the radiation laws. So here's Wien's displacement law. And if in case you're wondering, why is there, why does it, every sensor just about that you look has a 4 micron band, has a channel in 4 micron band. Here's the reason why. So if you have a forest fire, this comes from the Wien's displacement law, all you do is you do a little bit of calculus, you take this equation that's right here, and you just basically take dl lambda to d lambda, set it to 0, and that'll give you the maximum value. So you will find out that when you do the derivation, where you have forest fires, right, where you have forest fires at about 800 or 1000 K, the wavelength of maximum emission is about 3.9 to 4 micron. So that's really the reason why there's 4 micron bands in most of the channels. It's used for forest fire detection. So this is the sun's peak electromagnetic radiation. Here is forest fire, and here is the Earth's emission peak at 300K. So that's the reason why you have the Wien's displacement law. So getting into sensor characteristics, for those of you who are listening who are experts in satellite remote sensing, I don't want you to shudder at the fact that I talk about the spatial resolution as a square or a rectangle or a pixel. It's much easier to talk about it this way. So the characteristics that we need to be aware of: the spatial resolution, the size of the field of view, 10 by 10 meter is the size of a pixel. So MODIS pixels range from 250 meters to 1 kilometer. That is the spatial resolution. So just as an example, if you have low spatial resolution, it looks like this. And if you have high spatial resolution, you have a lot more pixels. So here are some spatial resolution examples: MODIS and LANDSAT and ASTER. And I'll talk a little bit about very high spatial resolution imagery at the back end of this talk. So spectral resolution is the next thing that we need to be concerned about. I talked a little bit about that, the number of bands. Some people define it that way. So for MODIS, there are 36 bands. It has 16 bands, so that could be the spectral resolution. I often like to talk about the spectral resolution as the width of the band. So for AVHR band 1 that I just mentioned, it's between 0.58 to 0.68 micron. Temporal resolution, how often the sensor acquires data. So for a sun-synchronous satellite, polar orbiting satellite, if you're only looking for daytime imagery, so it's once daily. So you have once daily. It's once during the day and once during the night. For GOES, it is every 15 minutes or so. Radiometric resolution. For those of you working with level 1 data, which is the the pixel level data, you can get data at 8-bit, which goes from 0 to 255, 10-bit, which is 0 to 1023, and so on. And higher the radiometric resolution, typically the sensitivity is more. For example, a long time ago, we did a study that showed that detecting jet contrails was a lot better at 10-bit data compared to 8-bit data. So radiometric resolution becomes very important. So there are numerous other factors that one needs to be concerned about that I won't get into here, which is spectral response function, point spread functions, calibration, and signal to noise ratio. But the only thing that I want to leave you with this slide is this. Everybody wants a very high spatial resolution data set, very high spectral resolution, a lot of radiometric resolution, and repeated data availability. So if you add all of that, actually you multiply all of that up, the data volume becomes really crazy. But more importantly, you cannot have it all. If you want to think about this, so for example, from this pixel, you need to get the appropriate number of photons for that particular band to have a certain type of a signal to noise ratio. So if you really go to higher and higher spatial resolutions, finer and finer spatial resolutions, higher and higher spectral resolutions, the data could be noisy. So there's a balance and a trade-off there as well. So again, here's a quick example. So MODIS, the swath width is 2,330 kilometers, which is the reason you have near daily global coverage. So in one day, you can get a global satellite data from MODIS with small gaps around the equator. But when LANDSAT, the swath width is very, very low. When the swath width is very low, which is 183 kilometers, it cannot cover the entire Earth in one day. It takes about 16 days for it to cover the entire day, and it is often called as a repeat cycle, a 16-day repeat cycle. So again, there's trade-offs between swath widths and spatial resolution as well. So the other key thing to keep in mind for those of you who are using level 1 data, and this is something that I always talk to my students about. So let's just say you're using MODIS data and your project is to calculate the area covered by each class. So let's just say area covered by vegetation, area covered by desert. The key thing to keep in mind is this: if your swath width is very, very high, for example, with MODIS, I just talked about it being 2,330 kilometers, the pixel resolution at nadir, for example, I'll use the 1 kilometer is pixels. The pixel resolution is 1 kilometer at nadir, but towards the edge of the swath, you will see that the pixel resolution is actually 5 kilometers, 4 to 5 kilometers. And that varies. So if you're calculating the area covered by each class, and if you're using the edge of the swath, you cannot multiply the number of pixels by 1 kilometer squared. You'll get a wrong answer. So the Earth's curvature and the panoramic distortion are very important when you use images with a very high swath width. Radiometric resolution, I'm not going to belabor the point. You can go from 8-bit data to 10 and 12-bit data. The ability to resolve certain features becomes very important with radiometric resolution, with high radiometric resolution. Okay, so let me talk a little bit about some of the things that are important for spectral signatures. You saw this graph before. Here again is reflectance on the y-axis, wavelength on the x-axis, and these are the fingerprints or the spectral signatures for each one of these features. So here's why radiometric resolution is important. So if you have a sensor that measures in a narrow wavelength band, which is in yellow, you're only looking at the feature that is primarily, if you're using grass or healthy green vegetation. But as the spectral resolution becomes coarser and coarser, you're not only measuring things that come from healthy green vegetation, but it comes from other features like soil as well. So you have mixed values. So that's why AVRIS has a lot of bands, so you can start looking at individual crops, if you will, rather than only broad classes like vegetation. So here is Landsat. You have the various bands. Again, we cannot go through every single feature of what this means. So most satellites have a red, green, and blue. And the reason for the red, green, and blue is you can form a color composite that is the same thing as your eye would normally see. And near infrared between 0.58 and 0.88, 1.57 to 1.65. The reason that those bands exist is because healthy green vegetation has a very, very high reflectance value. So you can separate vegetation from other features in the image using the near infrared bands. So this Cirrus band is rather special. Landsat added this much later. So people might ask the question, so what's the big deal behind Cirrus? So just about every newer satellite that has sensors has a Cirrus band. So Cirrus is sometimes so thin and very high in the atmosphere that it contaminates a lot of signal that comes from the ground or from other features. So this band 9 of Cirrus, the 1.36 to 1.38, is very, very unique in the sense that the radiation that comes from the sun is reflected by the Cirrus layer, and all of the radiation that goes below the cirrus layer is actually absorbed by the atmosphere and doesn't go out. So therefore, most of the signal that you see in the 1.36 to 1.38 micron band comes from thin cirrus. So that's absolutely, a fantastic discovery, if you will, by a scientist in Boulder a long, long time ago. And most of the sensors will have thermal infrared bands between 10 and 11 micron. We talked about that. This gives a measure of the Earth's surface temperature or cloud top temperature and so on. Again, here's a busy slide, but I'm not going to go through every single wavelength band in here. But if you start looking at MODIS and VIRS, which is a continuation, you will see that there are 36 bands here and there are 22 bands here, and there's lots of commonalities. If you take a look at Sentinel bands, there's lots of commonalities. It may not have all of the 36 bands. So again, red, green, blue is absolutely important. And then there's the ocean color. That could also be used to study phytoplankton and ocean color for ocean processes, to study atmospheric water vapor. But just about every satellite has this 4 micron band that we talked about, right? The 4 micron band. And thin cirrus bands are becoming major in most of the satellite sensors as well. So there's lots of commonality as you look through. So as hopefully after this lecture, if you start looking at the various bands, you will see some commonalities and you may be able to understand why these things exist. So this slide is just meant to show that just about everything has a spectral signature. So phytoplankton has a spectral signature. So if you have a lot of bands between 0.5, for example, here, and as the concentration varies, you can actually retrieve the chlorophyll, the phytoplankton concentrations if you were to use this kind of retrieval process. I make it sound easy, but it's not that easy. But at least that's the heart of using these bands. Again, you can do snow. You can study a measure of the snow grain radius. And here is the plot of reflectance versus wavelength for various snow grain radiances. And here are the spectral signatures for that. And finally, cloud and ash. So if you have a lot of volcanic ash, you need to be able to separate that from clouds. Visually, they may look the same. So most people are very fond of using things only the RGB or the visible part of the spectrum, but there are some really unique features in the infrared part of the spectrum. So here between 10 and 12 micron, if you see, so the y-axis here is not reflectance or temperature, it's something called imaginary index of refraction. You can think of that as absorption. Higher the imaginary part of refractive index, higher the absorption. So here's the key thing. If you were to take a look at volcanic ash actually decreases between the 11 to 12 micron bands, whereas the ice cloud and liquid water cloud have different spectral signatures. So if you know these spectral signatures, if you use these right bands, then you'll be able to separate volcanic ash from other features. So selecting the appropriate channels is going to be absolutely important. So therefore, only using RGB data may not be appropriate for all applications, especially for something like dust. It's not a good idea just to use the RGB data to separate dust into one of many features, because most of the signal comes from the infrared part of the spectrum. And sometimes you have to use the UV part of the spectrum. I'll show you a slide here in a minute. The 1.37 micron band that I talked about, again, is a fantastic find that is used to separate cirrus clouds from other features. So when the RGB or the true color composite fails, here is a false color composite that is used by LANDSAT quite a bit. The red, green, and blue, based on the physical principles that I just mentioned in the infrared part of the spectrum. So here is basically a visible channel, and here is this RGB composite, and you can actually see that the dust aerosols look pink in color. Again, this is just a visual representation of dust. And here is another thing, look at aerosol above clouds. Typically, sensors like MODIS will not give you any vertical information. But if you have the OMI, the ozone monitoring instrument, the UV part of the electromagnetic spectrum, these color values, these red values are actually smoke aerosol. Since the UV radiation absorbs dust and smoke, this is actually smoke aerosols that sits above the cloud layer, which has confounded scientists for a long time. But by combining two instruments, we can get a measure of the smoke above cloud aerosols as well. All right, so we know spectral signatures. Here's multispectral satellite data, and often we look at RGB, but you can look at false color composite. The first order of business really is to create a thematic map. So what does it mean? So you use the concept of spectral signatures or spatial signatures, if you will, and you use the multispectral data and you come up with a thematic map that separates each pixel in an image into one of many features, whether it's cloud, water, land, and aerosol. So usually this is the first step in image analysis. And there are many, many techniques to do that. So here's something from a class project from a while ago. So the left part here is the RGB. So here's a very, very detailed method that uses the normal probability distribution function using the maximum likelihood. A lot of you are probably aware of this, where you sit down and painstakingly pick training samples, and you have to make sure that your training samples are pure, they are correct, and you run it through a maximum likelihood algorithm, and each pixel in the image is classified into one of many classes. Where red is cumulonimbus, and these popcorn type clouds, these fair weather cumulus clouds, are shown in white, etc. So here is the clustering or an unsupervised classification where training samples are not necessary, and the same student actually combined maximum likelihood and clustering to provide a hybrid technique. So really, that's one of the initial techniques using training samples. So you cannot use training samples all the time when you're using a global algorithm. So for example, MODIS with all of its 36 channels, or GOES, uses all of those 36 channels and uses the concept of spectral signatures or spatial signatures, and they classify an image into one of many classes. It could be supervised classification, unsupervised classification. Principal or canonical transforms are basically rotating the axis, and then there are a lot of advanced techniques for complex scenes. Advanced techniques could be anything from neural network type of techniques to classify things like CIs. It's often very hard to classify complex images using spectral signatures alone, and therefore advanced techniques become very useful. So pixel to products, and I realize I'm at the 45-minute mark. I'm going to see if I can wrap this up as quickly as I possibly can before the hour. So here's level 1 data, right? So hopefully everybody is familiar now with what level 1 data is. So this is Swath level data, and this is a pixel at either 250 meter, 30 meter, whatever this is, and this is the Swath width. So I'm just going to give you an example for aerosol optical depth, because we work quite a bit with that, but pretty much most of the algorithms are the same. You take the level 1 data and you go through a radiator transfer algorithm. So again, please keep in mind, the key thing that the satellite measures is radiance, watts per meter squared per micron per steroradian. You converted that to reflectance or temperature. So now all the satellite has is a reflectance value, but you need to go to something called aerosol optical depth, or it could be cloud liquid water, it could be cloud particle size. So therefore, the radiator transfer algorithms actually go through a lookup table procedure and retrieves aerosol optical depth. So again, the key thing to keep in mind is there are many algorithms out there, many different products. So there's a 10-kilometer aerosol optical depth product, there's a 3-kilometer product, there's a 1-kilometer product. Various algorithms are used to create. So it depends on what product you want to use and for what purpose. So if you're using it for climate applications, you definitely would be using the 10-kilometer product because it's an overkill to use a 1-kilometer aerosol optical depth product. If you want to study air pollution, you'd be using the 1-kilometer aerosol optical depth product. So that becomes absolute key. So you've taken a level 1B reflectance and temperature. You've got a aerosol optical depth product that you have retrieved. How good is it? In this case, we're lucky. There is a ground-based instrument called a simul sun photometer that's around the globe. You basically compare the sun photometer aerosol, your independent variable aerosol optical depth with the MODIS retrieved aerosol optical depth to see how good or how bad they are. And often, people try to take the closest point to do this type of matching, but it's not a good idea because you have to remember that the sun photometer sits at the ground. It doesn't have really any spatial representation. So you need to average things in space and time properly. So for AeroNet aerosol optical depth, validation data exists and we're lucky, but it's not going to be the same if you want to validate cloud cover. That becomes a little bit tricky. I'll mention a couple of ideas for that. So here is level 1 data. It's a little bit grainy. Here is level 2, and the different colors of the different aerosol optical depth. So that's what it looks like. And then you can also very cleverly combine level 1 and level 2 data where the visible image is in the background. That's where the white color for the clouds come in, and you superimpose the aerosol optical depth on top of that. So key takeaway points: the conversion of level 1 to level 2, whether it's aerosol optical depth, whether it's cloud liquid water, cloud particle size, is complex and has uncertainties. Always, it's important to check the quality flags because depending on the type of quality flags that you use, your results will be different. So if you're studying aerosols, check for cloud contamination. If you're studying for clouds, check for aerosol contamination and land contamination and errors over bright targets, etc. I just pulled this from NASA's website. There are atmosphere products, land products, ocean and cryosphere products. And as you look through this, you can see there are a lot of products. And when it says aerosol products, there's more than one aerosol product out there. So it's really important to look at the algorithm theoretical basis document or the information that's on the data centers to make sure that you have the right data sets with the right quality flags to use. So I'm going to go through this very quickly. Rahul at one point talked about, a model, some of the modeling elements, what to watch out for. So the aerosol optical depth that one gets from the satellite is a columnar measurement. So it basically says this is the quote unquote concentration of aerosols in the column. So that is a good enough value for the climate community, but for the air quality community, you need to know what's happening at the surface because that's what we breathe. So it is really important to look at the physical interpretation. So here is the column aerosol optical depth, and here is the surface PM 2.5, and it's related through this equation. It looks very simple, but it's really gory. It depends on relative humidity, it depends on particle size, it depends on density, it depends on absorption. There's lots of things that are going on. So if you want to convert the column aerosol optical depth to surface PM 2.5, then you need to know what some of these geophysical parameters are. It's impossible to know, the vertical distribution of these aerosols, which is one of the biggest stumbling blocks. And this is a study that was done in 2003. Some people thought this was absolutely a ridiculous thing to do. Take a column satellite value and compare that with a surface PM 2.5 value. So all we were trying to show is, yeah, the relationship is linear, but this was 2003. There are more complex techniques that have happened now. But if you know some of the aerosol types and in certain conditions, a linear relationship holds. But the field has moved on in terms of how to do this modeling. This modeling has gone from linear modeling to nonlinear modeling, and it's a function of aerosol optical depth. the planetary boundary layer height, the temperature, the wind speed, and humidity, and so on. So ever since the dawn of the EOS era, so one thing I always remind people when I give talks at conferences is nobody ever thought that we will be doing surface PM 2.5 from MODIS. It was primarily designed to do climate and climate calculations, but people have stretched the limits of using satellite data, especially MODIS and MISR, to do surface PM 2.5 value. And in 2022 or so, we will have two instruments that will be specifically geared towards air quality. That's going to be absolutely fantastic. So again, the key thing to keep in mind is we went from linear to multivariate, and we went to a neural network type of an approach. This is gaining a lot of popularity, but still a lot of work to be done. Okay, so 2009 to now, the field has pretty much exploded, going from a linear correlation to multiple linear regression. And we are drawing from different aspects of other fields. Statistics especially has become absolute key. Generalized linear models, additive models, and the new thing that is being used, even in my group, is a geographically and temporally weighted regression technique. So rather than these regression relationships being static, they're actually dynamic as a function of time. And it really depends on how many ground-based instruments that we have. And machine learning techniques are becoming very popular. Most of the studies still use the conversion from aerosol optical depth to the PM 2.5, but there are studies that are also beginning to dangerously embark on using the measured values, the reflectance values, to convert that to surface PM 2.5. All right, validation of surface PM 2.5. So if you're doing surface PM 2.5, data exists. If you're doing AOD, data exists. If you're doing cloud liquid water, yes, there are some instruments on the ground. So some of those things are really easy. But if you're doing things like cloud cover, this is really hard. Yes, there are some cloud cover values reported in MET stations, but it's not exactly what the satellite measures. Frequency distribution of dust, again, that becomes difficult. So you have to use multiple satellite products to use for consistency. And there's limited aircraft data that's also available from various campaigns that can be used for validation purposes as well. So some caveats. Whenever using satellite retrievals, it's really important to make sure. So if you're using ghost data, for example, at high latitudes, the results are not, because of the oblique viewing angles, the retrievals are not as accurate as, closer to, the equator. And there are biases in satellite retrievals, so need to be careful with that. And some satellites actually struggle to provide retrievals of very, very thick smoke aerosols because they think it's clouds. So there are a lot of caveats that we have to look at with, the ATBDs, with the quality control flags. And finally, beware of cheap sensors. There are a lot of cheap sensors that are out there that are being used. So just be very careful with the quality of cheap sensors for validation. So this is from Janae Leroux. I don't know if she's in this call or not. This was, really rewarding. I hope it was for Janae as well. For me as an advisor, she used very, very high spatial resolution data to check, things like calibration and georeferencing and registration. So if you are using very, very high spatial resolution data that doesn't have good geolocation parameters or things from aircraft, the first thing you have to ask yourself is how good is the calibration, which basically means how good is the reflectance value and the temperature value that the product provides. And when they say that the latitude, longitude is a certain value, is it actually correct? So that becomes very important. So the data can be of very high spatial resolution, but can you actually create geophysical products, which means aerosol, PM 2.5, cloud liquid water, vegetation index, are the geophysical products of high quality? Finally, the important question to ask it, does it really make sense to create a high spatial resolution products? It may not be necessary sometimes. A very quick example of MODIS NDVI, so that it's just not in the atmospheric composition part. So here's the spectral signature we already talked about. Here's healthy green vegetation. And if you were to take the difference between the reflectance in the near IR to the visible part, the red part, you get an NDVI value. Here's another class assignment that actually calculates the NDVI value, which gives you a sense of the health of the vegetation. But again, if you have clouds, you see that you cannot get vegetation values underneath of that, right? Because these are optical measurements. So that is the reason why people create a 16-day composite. because on day 1 it may be cloudy, day 2 it may be cloudy, day 3 it may not be cloudy over this pixel. So once you create a 16-day average, you get a a complete picture rather than a blotchy picture of what the vegetation looks like. All right, finally the summary. Almost 1 o'clock. I didn't mean to talk this long. So since the dawn of the EOS era, tremendous progress has been made in earth science using satellite remote sensing. I didn't have time to show all of this. Even the IPCC reports have moved from only primarily a modeling framework to using satellite data in a lot of different places. Multispectral satellite data is still the golden standard for satellite image classification. Level 2 and level 3 geophysical products require a lot of radio to transfer algorithm work, and therefore it's really important to check the quality of the level 2 data carefully. Data fusion is also very important, especially combining coarser spatial resolution data with finer spatial resolution data and LiDARs and radars as well. Future sensors will continue to create products that are useful for research application and the community. So